Hello students, in this video we're going to work the next little problem set in the book, problems 9 through 16, and this is on page 18. And these are mostly graph related problems and then some other problems involving motion. So this problem 9 is asking you which of these four graphs, this one, this one, this one, and this one, represents motion at a constant velocity. And I've drawn these very small and abbreviated what the labels on the axes are just so I could fit everything on the board. So what this first one means, if I draw it in a little bit more detail, is I have in the vertical direction I'm measuring displacement. And then the horizontal direction, of course, is measuring time. And the way the curve looks is something like this. Now, does that represent a constant velocity? No. And an easy way to see that is to remember that velocity on a displacement versus time graph is the slope of the line at any given point. And you see the slope is changing. So here, this is small velocity. Here it's large. Large velocity. So it certainly is not a constant velocity, so that one's out. Now the next graph, they're trying to trick you because they draw a graph and then they have a horizontal line going across and you think, horizontal, it's constant. Yeah, it's constant, but it's a constant acceleration. So you have to pay attention to what the labels are. And then this is time going this way. Constant acceleration is certainly not constant velocity unless that acceleration happens to be zero. So the way in this case it's not, it's positive velocity. So the way the velocity graph would look here is it would look something like that. We don't know where it starts because this is just telling us how the velocity is changing. So this is the velocity graph you would get from this acceleration graph. It would look something like this. We don't know where it starts, so that would be a question mark because the acceleration is the change in velocity, and this is just telling us how it changes. It doesn't tell us where it starts out. But it does tell us it's positive the whole time. The acceleration is, and so positive acceleration means increasing velocity. And in particular, it's not constant, so this one's out. Okay. And then the next one is the right answer, and here they've drawn exactly the same graph, except now they're saying this is displacement going this way, and this is time, and that's exactly going to give you a constant velocity. And in this case, if the velocity is actually equal to zero, because, not only is so not only is the velocity constant, but the position itself is not changing. See, this would still be constant velocity if, if I drew, say this was velocity here, well, that would be a constant velocity. But the position would look like something like this, because it would be a constant positive velocity, which would be a increasing position. So this would be displacement, position, displacement or position. I'm using those words interchangeably. But this is an even more special situation. It's not only a constant velocity, it's a constant position. So this is, or displacement. I keep changing those words around. So it's not only constant velocity, it's a zero velocity, constant at zero. So that one is yes. And then the final one here, this is a very non-constant, this is a non-constant acceleration. It's an increasing acceleration. Well, if it's an increasing acceleration, then the velocity would be increasing even faster, and then the position would be increasing, even faster than that. So in any case, the velocity would not be constant. So this one is out. And so the only one that's constant velocity is this one, and that's C. So that's the answer to that one. Now moving on to number 10. What they're asking you, so this is a velocity versus time graph, and they're asking you what's the total distance traveled from time equals 0, so that would be 0 here up to 10. And I've drawn this, I've shaded under this because this is an area under the curve sort of problem. Now recall the distinction between area and signed area that I told you about in a previous video. So I could redraw this here, and this looks like this. And so this is 20 meters per second, and that goes down to minus 20. And then this is at 5 seconds, that's 0, 5, 10, 15. Notice how different the scales are here. This distance here measures 20, whereas the same distance going that way measures something like 5. So you have to pay attention to that. Now, remember total distance traveled. So this is like the number of steps that you're going. Total distance traveled is the area, not the signed area. So you're taking a total area. Now, we're only going up to 10 seconds. So I guess I should not really have filled in this part over here. We're only going up to 10 seconds. So that part plus that part there. So I could call this A1, I could call this A2, so that's A1 plus A2, so this is total distance is A1 plus A2. Remember, it's a plus because it's the total distance, it's not just the displacement. What would the displacement be, by the way, by the time you get to 10? Well, it would be 0. It would be where you started out, because the velocity, this whole time, this positive velocity is going to be canceled out by this negative velocity here. But we care about the total distance, not the displacement. So what is this area? Well, if I made this into a square or a rectangle here, the height would be 20, the base would be 5, that would be 100, but it's just half that because it's the triangle. So the A1 is 50, the A2 is the same, 50, and so the answer is 100. And that's choice C here. So that should be 100 meters. Okay. Number 11. What it does is it gives you a graph, a funny looking graph of velocity versus time. And it looks like this. The velocity is positive for a while, and then the velocity suddenly, abruptly changes to being negative. And I drew a little dot here and a little dot here. Remember, in the previous lecture, I'd drawn a position graph like this, and I told you this sort of thing was impossible in the context of position because the position couldn't instantaneously change. Well, the velocity is allowed to instantaneously change as an approximation. It doesn't really happen. It's more like a very steep change. It's more like, what would be more realistic is that it looks kind of like this. And then it's almost an abrupt change, but not quite. Anyway, it's a decent approximation to pretend that this is actually a vertical line, that the velocity actually changes abruptly. It turns the other way. And then it asks you what would this graph here describe? And it gives you some, and I'm going to cheat and look back and see what it says. A person on a bike accelerating in a straight line and then decelerating. No, certainly not. That would not look that way at all. So if this was velocity, this was time. A person on a bike accelerating and then decelerating, the way the velocity would look is the velocity would increase for a while and then it would decrease. It would certainly not start out like this and then jump. And then it says a baseball thrown by a pitcher and hit by a batter. And that turns out to be the right answer. This is answer B here. What's the sense of this? Well, the point is that the velocity is changing to the opposite of what it was. It's very rapidly reversing direction. And that's what happens in a pitch and hit. So the ball, so here you have the baseball, and it's heading this way, so this is on the pitch. And then when it hits the bat, so, when it hits the bat, I don't know if I can draw a baseball bat. This is like a sorry representation of the baseball bat. When it hits the bat, it's going to go back the opposite direction very quickly. So if this was the positive direction here, when it hits the bat, it's going to reverse. And so that's why it's going from positive abruptly to negative. And then the other choices were a planet in orbit, and that's obviously not going to make any sense. In this case, so a planet in orbit, here's the sun, here's a planet, I'll say P for planet in orbit. Well, here the velocity is changing. It's staying about the same magnitude, but it's changing direction. But it certainly doesn't look like this abrupt sort of change there. And then the last one is the swing on a pendulum, or one swing on a pendulum. And again, that's not a good description because that's something that's changing gradually. The pendulum will come to a stop, so it will, at the bottom. So here's your pendulum, and it swings like this, and then it swings here. So it's going here, and then it's going back. One swing of a pendulum, when it gets out to this point coming this way, it stops, and so that there the velocity would be 0. And then the velocity would be increasing for a while, and at the bottom it's going the fastest, and then the velocity is going to decrease going this way. And so that would look totally different than what this does. So here we had BU as the right answer. Now for number 12, you're given a graph of position versus time. It's a very simple graph. It's going this way. I'll say displacement here. I simply cannot seem to avoid saying position instead of displacement. That's what I'm used to. But this is time going this way. And so what it's asking you is which of these variables are increasing? Is the position increasing? Is the velocity increasing? Is the acceleration increasing? Well, here you've got, remember I told you if you have a displacement versus time, the velocity on there is the slope of the graph. And the slope is staying the same. Here, same slope, same slope the whole time. So you've got x is increasing. V is constant because it's the same as the constant slope. Acceleration is 0 because that's what it means for the velocity to be constant. That the velocity is not changing, the acceleration is 0. So the only thing that's increasing is x, and that's answer choice A. Okay. 13. So they give you a graph of velocity versus time, and they give you a list of statements, and they say which of these statements is not true about the graph. And so if I recopy the graph over here, it looks like this. It goes up for a while here, and then it's constant here, and then it goes back down like that. And this is a height of 5, 10. This is, let me say 0 there, 5, 10, 15, and this here is time, and this here is velocity. So we can ask which of these statements are true. Is there 100 meters total displacement? Well, you have a velocity versus time graph. The displacement is the area underneath it. The area is all above the axis, so there's no like signed area thing. By the way, if there was part of the area underneath the axis, you would have to use the signs because we're asking for displacement, not distance. But what is this area? Well, I can figure it out by adding up the area of this triangle and this square and this, or rectangle, and this triangle here. What's the triangle? Well, this is a distance of 5 there. Height of 10, that's 1/2 base times height, so that's 1/2 5 times 10, so that's going to be 25. And then this here is just going to be a base times height, same base times same height, so this is plus 5 times 10, so that's plus 50. And then we have a triangle of the same size, 1/2 base times height, 1/2 50, so it's going to be plus another 25. 50 plus, or 25 plus 50 plus 25, this is equal to 100. And so this one is true. This one is true. Now, when I'm putting check marks here, the question, of course, asks which one is false. When I'm putting check mark, it says it's true, and so we're going to figure out which one of these is false, and then that's going to be the one that we isolate. So the second question is the acceleration constant from time equals 0 to time equals 5? Now that's this interval here, moving from here to here. Now you might look at it and say, well, it's not constant because it's increasing, but that's the velocity that's increasing. And a constant increase in velocity is acceleration. The acceleration is constant because the line is straight. See, here you're thinking slope again. The slope here is constant here, same slope here, same slope here. The slope of the velocity curve is the acceleration, so you have a constant velocity. Yes, this is true. All right, I mean constant acceleration. Now, the next one is there a constant velocity from 5 to 10? Yes. Here you're reading this right off the graph, because the graph is velocity versus time, and this is a constant velocity from t equals 5 to t equals 10. So that's true. And then the final question is the particle moving backwards from 10 to 15? That's this interval. They're trying to trick you because you see the graph is going down like this, and so they're thinking, oh, down, it's moving backwards. But the particle moving, whether it's going backwards, that's talking about how the displacement is changing. And this is not displacement versus time, this is velocity versus time. See, this whole time the velocity is still positive, and that means the displacement is continuing to increase. Remember, we figured out that over this interval, in fact, the displacement increases by 25 meters. Here it was 50, here it was 25. So, no, it's not going backwards, it's continuing to go forward. It's going forward and slowing down. That's the point, it's slowing down. So this one is false. That's the only one that's false, and that's answer choice D. Okay. So those were all kind of conceptual problems. I guess you had to calculate a few areas, but mostly not so much using equations. Moving to 14, here we would use an equation. And what this says is you have a cliff or something, and the cliff is 40 meters tall, and you throw something off or launch something off horizontally. So this says horizontally. So it's horizontal launch or throw or something like that. And the question is, how long is it going to take to hit the bottom? So this is going to go down like that. So it's going to be a parabolic trajectory. Draw that more accurately. It's going to be parabolic trajectory. It's going to hit the bottom. Now, the thing to realize is that the fact that you've thrown it off horizontally and how fast you've thrown it off horizontally is totally irrelevant, because the initial vertical component, the fact that it's horizontal, means that the initial vertical component is 0. And that's all that determines how long it takes to fall. See, the initial y velocity is 0. So it's 40 meters, and so you're asked for the time. One way to solve for the time here would be to say that, remember we had this equation x minus x0 equals v0 t plus 1/2 a t squared. Here we really, I guess we have y. We could call this x and we could call this y here. And so we're really looking at y. And so we have y here. And the initial velocity is 0, so we don't have to worry about that term. So we just have a 1/2. Now the g, that the velocity due to acceleration is g, so that's 10. I guess what I'll do is I'll start it out at I'll say this is a height of 40, and it falls to the bottom. So if this is y minus y0, then this would say that the final y is 0, the top y is 40, and then we're going to have a 1/2. So this is g. You can put a minus sign in there or not, depending on what you want to call it. But in any case, this comes out to 1/2 and then minus 10 and then t squared. And so what do you get? You get over here minus 40 equals minus 5t squared. Divide both sides by minus 5. I get 8 equals t squared. So t is the square root of 8. If you want to change this to 2 square roots of 2, and that's about 2.8. And the answer choice they give you is 3, and this is close to 3. And that's the smallest answer they give you, so you couldn't wonder if it's actually the right one. It comes out to 2.8, and that's answer choice A. So that's how you would solve that one. All right, and then 15. It says you have this mass, and it's a 10 kilogram mass. And it says that it's in free fall, and it's accelerating downward at minus 10 meters per second squared, because it's gravity. So I've just written g here, that's the minus 10 meters per second squared. And it says what you want to do is you want to reverse this motion. So you want to not only make it stop falling, but you want to make it go up, accelerate up at plus 10 meters per second squared. And the question is, well, how much force do you have to exert to get it to do that? And it turns out that the right answer is 200 newtons. And how do you get this answer? Well, it's 10 kilograms, and then the acceleration downward is 10 meters per second. So to cancel that out, you would have to apply 100 newtons. If you applied 100 newtons, then it would no longer be accelerating at all. It would be completely, it'd be moving at a constant velocity. The force due to gravity would be completely balanced by the 100 newtons going up. Well, but we don't want to do that. We want to actually reverse it. We want to make it accelerate up. So now you have to exert enough force not only to cancel the downward force due to gravity, but to exert enough additional force to make it accelerate up at the same rate as what it was accelerating due to gravity. This comes out to 200 newtons, and that was answer choice D. And then the last one is a trick question. This is number 16, and it says, so you have big skydiver and little skydiver. So you have, here's my terrible artwork. So here's the big skydiver with its parachute, and you have the little skydiver with its parachute. Okay, and it says that this one, so this one was, I think this was 100 kilograms, I'm not sure. This one's 50 kilograms. And it says they both reach terminal velocity. Well, it doesn't say terminal velocity, but that's the way you usually describe this. It says a constant velocity. So the idea is that it accelerates downward until it's moving fast enough to where the wind resistance is enough to prevent further acceleration. So it's going downward at a constant velocity. And it says, well, is the net force on the bigger skydiver bigger or smaller than the net force on the smaller skydiver, and why? And so this is sort of a trick question about net force. It turns out that the net force on both skydivers is 0. Why? Well, because they're not accelerating. So this is, Newton's second law, which we haven't really talked about yet. But force equals mass times acceleration. If the acceleration is 0, because the velocity is constant, then this says that the force there has to be 0 as well. So the answer is that they both experience the same net force, but it goes further than that. Not only is it the same net force, the net force is 0 on both of them.